Good morning to all of you. Good morning, Manu. I hope you can hear me clearly and see my screen. Today's class, we will, I have planned in two parts. Part one is on YouTube Live, that is some of the problems we will be doing or at least looking at. And in the next part, after we finish that, we will meet on Google Meet. And since DIP projects are starting, we will have a look at the recommended projects, and if you have any doubts or clarification, then we will talk about it. So going ahead with problem sets, if you have some pen and paper handy, keep it near, you may need it. So here is my first problem. All the problems I have taken from the book only, and we will stick to the book problems, most of it. So going ahead, you have been given a picture. Give the percentages of red X, green Y, and blue Z light required to generate the point labeled warm white in the figure. The figure has been provided. If you recall, this was the chromaticity diagram. Remember, the problem solving always gives an opportunity to recall the theory, revise the theory, understand it better and deeper. So don't shy away from the problem solving part. In fact, as a student of as a student in general and as a master student in particular, you must attempt as many problems in physics and in the subtopics as possible, because after MSc you will not get this opportunity to enhance your problem solving skills. These are the last 1 year or 1.5 year of your education where you are getting a systematic opportunity to enhance your problem solving skills. Please don't shy away from it. Try to solve as many problems as possible. Try to solve them on your own first. If you are unable to solve them on your own, then either look at the references or your friends or your teachers, whomsoever, but see to it that you practice more, because after you pass out from the MSc, your you are not no longer part of any course, any structured course, unless you plan to do another MSc or something. You are no longer part of any structured course, and obviously there is no mandatory requirements on you to solve the problems. You might do PhD and others, but then you will be very much focused at one or two problems, of course large scale problems, and also maybe in one field, just one subtopic, and not an array of problems related to various topics. So as I said, it's a wonderful opportunity and the last opportunity, so you must practice as much as possible so that when you go out you are fairly confident. So what about this problem? So this is a chromaticity diagram. If you remember, in chromaticity diagram we plot red on the x-axis and green on the y-axis. We also recall that it is calibrated between 0 and 1. So from 0 to 1 it is here, from 0 to 1 it is over here. When it is 0, when the red is 0, red is absent. When red is 1, red is maximum. Similarly for the green. Remember, these are normalized scales. In practice, the red and green scale, if it's an 8-bit, then it will vary from 0 to 255. So here 0 is taken as 0, but 255 is taken as 1. So the question is, give the percentages of red, green and blue light required to generate the point labeled warm white. So if you look at the warm white is somewhere here. So looking at this chromaticity graph, I can easily figure out my x and y coordinate. So if you drop a perpendicular from here, you may drop a perpendicular say somewhere here. So maybe I can take, see this is zero point 0.4 and this is 0.45. I may take it as 0.41. So my x value will turn out to be 0.41. What will be my y value? So I can take again and take an approximate here. So it is again a point, or maybe I'll just take it zero point 0.4 here. So my y value is zero point 0.4. So remember, these values multiplied by 100 will give you percent. So 0.41 will give you 41% and y value is zero point 0.4, that will give you 40%. So it has 41% of red and 40% of green. So together they will give me 81% of red green. Then how much is the blue? You know that if you subtract everything from 1, you get blue. Or in percentage term, if you subtract everything from 100%, then you will get blue. So 100 minus 81, that will give you 19% of blue. So that is a warm white. I mean, there was a time when artificial light sources uh, getting cold white, cool white, and warm white and daylight was very challenging. In fact, long back, you used the filters were used to be the only cheapest source to create these shades. But present day LED technology offers all these shades of light at a very decently cheap pricing. So if you are a light enthusiast, all you can do it at your home. If you have 2 or 3 rooms, kitchen, bedroom, bathrooms, hall, living room, etc., you can buy LED bulbs of different shades. So they are available in daylight, cool light, warm white, slightly yellow, all colors they are available. Not very expensive, 100 rupees. Depending on the wattages you buy, around 100 rupees, 120. And you can place them in different rooms to get different effects. Just to make your point, if you look at point of equal energy, then this is somewhere here. Now equal energy is 33%, so 3.33 here, and if you go on this scale, then again 0.33, and you subtract from 1 the sum of x and y, you will again get 0.33. So that is where neutral or equal intensity. Daylight, normal sunlight, say at this time if you go out, it is not of equal intensity, it is slightly more towards the bluish end. So if you take this, then this is around 31%, green is around 32%, so together it is around 63%, and the blue will be around 37%, more than 33%. So that's how the daylight is composed of. Okay, let's go ahead. So I have another problem here in front of us. The RGB component images of an RGB image have the horizontal intensity profile shown in the following diagram. What color would a person see in the middle column of this image? So I have some image whose graph of color versus position has been plotted. So this is it's a gradient image. You can see this is This is x-axis or position. On this side, red is very bright, 1 maximum. As you go on to the right edge, the red value decreases linearly and becomes 0. Then how does the green profile vary? So green would be 0 in the beginning, goes on increasing at the end, in the middle maximum, and then again goes on decreasing. How does the blue look like? So blue has a 0 in the beginning and maximum at the end. So this is my original image. Original image is a single image and we have split its RGB profile. What color would a person see in the middle column of this image? So how do you get this? So that's a very straightaway calculation. You can see that in the middle, the red has the middle value, 0.5. In the middle point, midpoint position, the green has 1 and blue is again 0.5. So obviously at the midpoint in the image, the red is not that strong. It's half as strong as of its maximum. Blue is again half as strong as of its maximum. So, and green is maximally strong. So obviously the image would look dominantly or predominantly green in the middle. I think I have a little demo to take this point ahead. So let me just show you. I have a rectangle here and I will have an RGB profile to fill it. These are my RGB sliders. So red is halfway. Remember, this is 0 to 1 and I'm using 0 to 255. So halfway is 128. So I can put 128. And blue is also halfway. So I can put the blue slider at 128. So both of these are at 128. The green slider is at 1. So green I'll put at 255. So this is 0.5 on a scale of 0 to 1 or on a scale of 0 to 255, 128. This is 255 halfway through, sorry, full way through, and this is again halfway. And you can see that it looks dominantly green. So that is how the midpoint would look like. You can always ask this question for the other positions too. So for example, if I ask this question that how would it look at the origin here? You can see red is 1, green is 0 and this is 0. So it will look red. How would it look like at the other end? So it will look blue because red is 0, green is 0 and dominant is blue. How would it look like 1/4 of its distance from the origin? So at around 1/4, 1 is 0.75. So maybe to this I'm adding 64 more. So it will become 92. And at this middle point, this will be zero point 0.5. So this becomes 128. And at 1/4, this becomes around 64. 64. So you can see this is the color that will appear at 1/4 of the distance from the origin. So that's how it colors will change. It would be very interesting to draw the entire image or paint the entire image. So try doing it. Leave it that, take that as a work. You can try painting it from left hand to the right hand. Okay. Going to the next question. What is the maximum number of possible different shades of gray in an RGB image whose three component images are 8-bit? Can anyone answer this? That's an easy question. You have an RGB, red, green, blue. Three components will be red component, green component, and blue. It's an 8-bit image. Since it's an 8-bit image, I assume that all the three components, red, green, and blue, all the three are 8-bit only. So all the components are represented by 8-bit. How many possible shades of gray could be there? So can you quickly answer this? Remember, there was a time when mobile phones were new initially. They they were sold by using this parameter, that how many shades of color or how many shades of gray does a screen represent. So initially it was only 8-bit, and then later on it moved to 16-bit. The number of colors shown were very large. So some million colors could be represented. So think about your answer here. Manu, no, that will not be the correct answer. Think a little more. Okay. So the correct answer to this problem is just 256. Remember that if you are looking at the shades of gray, a gray color is created. Think when. A gray color is created only when all the three RGB they are mixed in equal proportion. Any of them is less or more, the color will no longer remain gray. Suppose if red is slightly more, G and B are equal, then it will be reddish gray but not gray. True gray will have all the three components of the same value. Now, so RGB, if all three are 0, you get darkest gray, which may also call as black. If R, G and B, all three are, say, they are 8-bit, so if these three are 255, 255, 255, then you get the brightest gray, which you may also call as white. And then any intermediate value. But remember, RGB, all three must have the same value simultaneously. So if R is 200, then G should also be 200 and B should also be 200. So 200, 200, 200 will give you a shade of gray. Okay. I think we can have a little demonstration of a similar type here also. So again, I have this rectangle which we are going to use to produce this demonstration, and again I will use my RGB slider. You can see that right now RGB slider all three are 255, 255, 255, and this looks white, a brightest shade of gray. Suppose I destroy one, say I make it 250 in my blue, then what happens is that neutrality is lost. Now you may see or you may not see on your screen depending upon the kind of calibration you are using, but this is not pure white. Let me see at what scale it is visible. Suppose I make it 240. You can now see that this is slightly reddish hue appearing now. Let me make it 230 and see. So I'll slide it slowly and decrease it, and you can see that the other colors dominate. So that's the whole idea here, that you are now decreasing blue and keeping red and green highest, the other colors dominate. If you decrease green, then the other colors dominate. If you decrease red, other colors dominate. So in order to maintain the gray, you need all the three shades to be equal. I'll show you some example. Suppose I put 200 here. Now you can see that it's no longer the gray, but the moment I make all the three equal, it again turns out to be gray. This is another gray. I make it go to the halfway through 128, putting 128 here and putting 128 here. And this is when all three are equal, once again it's all gray. Just to complete my demonstration, let me put 0 everywhere. So my red is gone, only blue and green, so blue green color is appearing. Another 0, so only blue remaining. And I put this also 0. What will happen? All the three will go, so it will be black. So the black appears. So all the three, when they move together, you create different shades. So in a 0 to 255, you will create around, say, 256 different shades of gray. Okay, that's good. Let's go ahead. Propose a method for generating a color band similar to visible spectrum. 2 is missing. So this is an algorithm. Remember, we are doing computer programming. Computer programming starts with algorithm. You write basic line by line algorithm, then convert it into a more detailed flow chart, and then finally write your code. So here is your question. Propose a method for generating a color band similar to visible spectrum. So all we want is our output to be equal to this band. It should look like this. So you can see that doing this is, you can do it in RGB, you can do it in HSI. What do you think? Which model could be better, more handy, RGB or HSI? So the more handy model over here is going to be RGB. Why RGB? I'm sorry, HSI. Why HSI? Because here you can see that you are only looking at the hues, different hues. You start with magenta, although not clearly represented here. It goes into a violet, blue, green, yellow, orange, red, and I would say that suppose it ends again at magenta. And there's the complete color wheel that we had spoken of in the last class or last to last class, I guess. So all you need is different shades of hue plotted with position. Scale one can decide. So HSI is going to be the key model which will solve this problem easily. You can do it with RGB also, no issues, but then you'll have to do a lot of calculations, more calculations, because RGB you have to calculate magenta and intermediate colors. In HSI, I just make some simple assumption. I make assume that all the saturation is maximum. So S is 1, that is a constant parameter now. Assume maximum intensity. So I is also 1. So another constant parameter. So two constant parameters are now established. And I just have to plot hue versus position. So different hues can be plotted with position. You remember the hue scale starts from the red, ends at red. In this plotting, you have to start at magenta and end at red color. So that's how a hue scale looks like. You are plotting at maximum saturation, so you are plotting at the border of this. You start your plotting, say, from magenta, so it's here, and then you go anti-clockwise sense, so magenta, blue, green, yellow, and red. So you plot take your angle theta, hue angle, and you plot it against the position. You can select your scale in Python or whichever software you're using, and you can get done with this. So very simple, straight away things to plot. By the way, in today's practical session, you will be taught to handle color images in DIP or in Python. There's another image. The following 8-bit images are HSI components from the, we have know this these color wheels. So I mean, this is red, this is green, this is blue, and these are the mix. So everything is mixing together to create your white and blacks. The numbers indicate gray level values. Answer the following question, explaining the basis of your answer in each. If it is not answered, possible to answer a question based on the given information, state why you cannot do so. Give the gray levels of all the regions in the hue image. So this is a hue. Whenever hue is 0, I'll just give you some hints. You can solve it. When the hue is 0, then you are at red color, so this has to be a red color. So you have to refer to figure 6.14 in your uh, in your book reference. So if you are red color, at red color, the hue is red. At 0, at 43, you will get some yellow orange. As you go higher, you get green. You are heading towards magenta, I'm sorry, cyan and blue, and then towards magenta and back to the red. So you can predict the values by adding or subtracting in the circle. At the center, your hue is again 0 if it is black in the original image. Your hue is uh, if it is red, then hue is again 0. If it is towards magenta, then the hue is maximum. This is saturation image. This is 0. This is 255. Most likely this is going to be 0 again. And this is the gray levels intensity image. At the center it is 255. At the periphery black is 0. This is 85. This is 255. Now you can have different calculations. So figure out uh, this has to be 255. This area is the sum of this region and this region. So you can assign some value, say x, y, then x plus y is 170. This you can call z. You can say x, y, and z is 255. And then figure out how much is the z value, how much is the x and y value, and solve for other two parts also. So that also I leave it. It's a simple problem rather. I leave it for you people to finish it off. Now with this, I think I'm finishing my problem discussions here. We will now meet at the Google Meet and take up some of the discussions for project work. Thank you.